Okay, welcome to today's lecture on routing. Okay, so this is an example which was taken from one of the books. Now I want to walk you through. It will be a bit, long lecture because I want to be slow so that you understand. Example. So after this one, I think as you see, there is a part which I will introduce you to. It's also one of the ways that you can solve this problem. So I'll give you another, perhaps in part 2. I'll give you a brief explanation on how you go about it. Now, okay, for now let's continue with this one. The elevation, outflow, discharge and storage data for a reservoir are given in the following table. Okay, the elevation, okay, the elevation here, okay, sorry, okay, it's happening. Okay, so the elevation, which is this one here, the storage, the outflow are given in this table, okay, or the discharge is the outflow. An inflow hydrography given below, this one here, enters the reservoir when the initial water in the reservoir was 63 meters. So the initial conditions are very important when routing. Okay, now this is the inflow hydrography. There is time and then the inflow. Okay, and just understand, writing it's okay. Now question: route the inflow hydrography using the modified pools method and determine A, outflow hydrography, B, maximum reservoir elevation during the passage of the flood. Okay, this I think I will talk about this in the part 2 of the video. Okay, C, peak outflow discharge, attenuation, and E, time lag. These are the definitions that these are some of the key ways which we defined in the previous lecture: attenuation and time lag. Okay, from the reservoir. Plot the inflow and outflow hydrograph on the same graph sheet. All right, so solution. The first thing that we should bring in mind and write is the formula. This formula here. Okay, this formula here. Okay, this formula here is very important because this one then guides you on how you're going to draw your table. Routing seems to be complicated, but trust me, once you understand how to put the variables in your table, then you are done. It's very easy, simple and straightforward. Okay, now we'll come back to the formula first. Now the first thing that you want to do is to create the relationship. Okay, to create the relationship between storage, outflow, and time. Okay, or in other words, you need to come up with an indicative storage. An indicative storage, this one here. Okay, in most cases you may not be given, but sometimes you may be given. Now, how is this calculated? So this, you get these figures. There is a storage here. Okay, there is storage here. Okay, then also there is outflow here. Okay, then there is also now this one here wasn't really necessary for now when creating this. Okay, now to find this one, you have your storage. For example, at t is equals to 0, you start now creating indicative storage. At t is equals to 0, your S2 is this here, this number 3.55, and then your Q2 is this one, which is 0. Okay, then the change in time is gotten from these values here, the change in time. Okay, now in most cases this I think they try not to complicate things, but this then is given as a constant difference in times. Okay, maybe for example in this case is 3 hours. It's continuously 3 hours all the way up to the end of this reservoir, you know, this flood movement. But then sometimes at a certain point in time it might change, so you need to be very careful. You don't need to take that mentality that all the time it is the same. Okay, now why these small intervals, time intervals? This is trying to make it linear, but then we understand that is not how things are. It's trying to you know, study or understand the flood as it moves, or the inflow as it moves in more like a linear manner. A very short period of time is linear. You then within that period, the interval, you finish and you enter another one. It's more like it's a straight you know, straight movement. Okay, a straight yeah, a straight movement. Okay, now so for example this figure was calculated, I think, okay, I indicated here. Okay, here, see. So S2 plus Q2 change in time over 2 is 3.35. This figure here for t is equals to 0 plus 0. This is the outflow. Okay, 0 times change in time is 3 hours. Make sure you convert 3 hours into seconds, hours into seconds, because this is a storage and this is meter cubed. So we need to cancel this meter cubed per second, remove the second by multiplying the change in time. So the time must be in seconds. Okay, then this 2 is this 2 here, but then you have multiplied the 2 by 1 million, because if you look at the storage here, you know, you learned like terms. This thing here is in million cubic meters. Okay, million cubic meters. So we want to make also this other part to be million cubic meters. That's why we are dividing it by a million. So now, because this is 0, this whole term here becomes 0, and then you end up remaining with this figure here, which is 3.5. So this calculation is repeated for all these values here. Okay, so for t is equals to 2 here, you have your storage as 3.5, which is here, plus now your outflow is 10. So you have 10 times 3 times 6, so which is 3 times 60 times 60. I think this should be one is it 800 seconds. Okay, so you multiply that by this, and then you divide by 2 million. You have 3.3 is it 3.35 3.554. okay, is here 3.554. okay, let me just remove these. Okay, so this is how these were calculated. I'm sure by now you are clear. So bear in mind that these two, this column here and also this guy here, they are not yet they are not useful at this moment when you are creating these relationships. Okay, now sorry, the second thing, now that we have created this relationship, is very important. Remember we said that we want a situation where from this information here, then we can create on the graph okay, which I'll talk about later. Okay, now this is the table that we have for all our calculations. Now these things that are put here, this part here, this part is nothing but this formula here, okay? And that's the beauty part about the table, okay? So we have our time here, we have our inflow hydrography. These are the things that were given in the question. But then in the formula we have this, we have this, okay, and also we have this. Now before we come to this one, then we need an average so that it becomes easy. We need an average of the inflow, and then we multiply it by time, okay? Then we have one part, one component. This one remains as it is, this one remains as it is. So that is why here you realize that we have two, this one and this one, but basically it was just supposed to be, if I wanted, I would have just written it like this. So meaning I would have just added the inflows, divide by 2 and multiply by time straight away. But then I wanted you to see, we put these ones, find the averages first, then just multiply the averages by time, okay? Yes. Now so from here, this is 10, 20. So the average is simply you're adding 10. You're adding 10 plus 20 is 30 divided by 2, 15. 20 plus 55 divided by 2, you have this 37.5. 55 plus 80 divided by 2, you have this value here. This value plus this value, you divide it by 2, you have this value here. So that is how all these have been calculated, okay? Then now that we have the averages, then we can multiply by the time, okay? The change in time, remember, is 3 hours. So we convert that into seconds. We have 10,800 seconds, okay? We have 10,800 seconds, okay? So when we multiply this, now remember, always remember to check the units. So when we multiply this time by this one, we'll have meter cube. We have cubic meters, right? Now if you look at all these, they're in millions meter cubed, million meter cubed. So this one also, to make it million meter cubed, then we divide it by 1 million, so that we have this meter cubed, million meter cubed, okay? So then after multiplying by the time, we have this column here, okay? Then so this is where we end with what we know. Okay, so initially the table, when you draw your table like this, the values that you are going to put first are these, because these you know, okay? Because these you know, these here, these will be your first values. This table will be filled with these values first, because you know the time, you are given the question, you know the inflow. This is just this same inflow, but you're finding the averages, and then because you know the time, you're just multiplying it, you fill in this. Now the real calculations start here, okay? Start from here, and this is now where we want to explain, so that you understand. I'll be very slow, okay? This will be a long lecture, so that you understand, okay? Now the first input in your this column here is from the initial conditions. Remember, I said initial conditions are very important, okay? Is from your initial conditions. And what are our initial conditions? The initial water in the reservoir was 63 meters. So when this inflow entered, entered into this reservoir, the initial water level in the reservoir was 63 meters. Okay, now 63 meters, what do we have at 63 meters? Okay, 63 meters is here. This is the elevation. 63 meters is here. Okay, so what do we have? We have the storage at this particular moment. We also have the outflow, which is 20. Okay, then now the first entry is coming from those initial conditions. So how? By simply putting in those values that we have been given. So S1, which was I think 3.88, we put it here. Okay, 3.88, we put it here. Then minus Q1, it was 20, right? It was 20, we put 20. Then change in time is constant, which is 10,800 seconds. Okay, then over 2. Now remember also to convert this part here into million cubic meter. Therefore this will divide by 2 million, because we are multiplying this over 2 here by a million, so that then we can subtract, because this S here, S1 is in meter, is in million cubic meter. So even this part will convert it into million cubic meter. So you multiplying Q1 by T, you are just converting from meter cubed per second into meter cubed. Okay, now then you go further and convert that into million meter cubed. Now when you put those values, so here we have okay, so here we have our 3.88. okay, then minus Q is 20, then times 10,800, these are seconds, over 2. Then you want also to convert this into a million. Okay, into million. Okay, so when you punch this number into your calculator, you have this value here. Okay, now let me just remove this. Okay, now when we put this value here, what does the formula say? The next value we need to put here. So but what does the formula say? The formula is telling us that we add this here plus this here to get this here. Remember we said all these are known variables, and that is what we meant, because we know the inflow, we know the time difference. Then from the initial conditions we have these. Okay, so then everything here is known. So to find this unknown part, we just add the way they are. Okay, now since we know we have already, we know we have just calculated here, this part here is, we have this one, and then this part from the initial conditions we have this value. Then we just add this plus this, we get the unknown. Okay, now let's pause a bit here. We have the unknown, right? But how do we get the Q2, which is the main focus? How do we get this one? Now we get this one either using the graph or linear interpolation. Now here, because I don't have a graph paper, so I had no option, so I used the linear interpolation. The graph part, how you can find these figures using the graph, I will explain in part 2. Now let's focus on linear interpolation. How and when do you use linear interpolation? You can only use linear interpolation if and only if there are a set of numbers such that x1 is less than or equal to x less than or equal to x2. x1 is less than x and x is less than or equal to x2. Now, which one is your x? And each one is your x1, x2, and x. Now, your x is this thing here. This thing here. This is your x. Okay? This is your x. Now, we have this x here, which is 3.94. So, where do we find those two sets? X1 and X2, and these X1 and X2 are coupled with the Y1 and Y2 values. Now, where do we find those? Then you come back to the relationship that you were building. Okay? You remember the relationship that we built here? Here. This is the relationship that we are building. Now we come back here, we say, okay, now this also, this part here, this is now your set of x1 and x2. Okay, this here, the same indicative storage that we were calculating. Okay, now we said the figure that we have here is 3.9. Do we have a set of two sets which are following each other, where you have a number less than this value and a number greater than this value? Of course we do. And those figures are 3.55, because 3.55 is less than 3.9. So we have 3.55, this value here, and the 3.98. Okay, 98. So this figure here, this one here, this one is in between these two, and it satisfies this condition. Then we can do linear interpolation. Okay, and these two values here are coupled with the y values. Now you understand very, very well when I start explaining on the graph. Okay, now, so since we have these two, then we can find the value of q, because the next value that we need to find is q2, this one here. Okay, for now let's forget about the elevation, because using linear interpolation, unless we complicate the calculations, we can calculate it, but it is easier to use a graph, because when you're using a graph, you're finding the value of q and the elevation at the same time. So for now, forget about the elevation. We explain in part 2. Now, let me just I don't think if I included it here. Let me see. Let me check down. Okay, it's not there. Let's calculate it together. It's in the paper that I was calculating. Now, so this is the equation that we are using. Then we have, I need to be seeing the values. So we have, let me see if I can okay, can I rub this? No, okay, let me not rub it. Now we have, let me just come here. So we have y, which is q2, okay, is equals to y1 plus y2 minus y1 over x2 minus x1 times x minus x1 minus x1. Okay, that's it. x1. Okay, so then what is your y1? Your y1 here is 10 here, 10. Okay, your y1 is 10 and your y2 is 20. Okay, so you say y1 is 10 plus y2 is 20 minus 10 over So you come to x part, the x part which is this one here, you have x2 which is 3.98, the bigger number, minus the smaller number 3.554. So minus 3.988 minus 3.554. Okay, then times z. Now your x value is this one here, on the here, not the indicative storage, but the one that we are finding here. So which is 3.94 minus 3.554. Okay, so if you mess around here, you get a negative. So you need to be very careful. And then when you punch this whole figure, you get this number which we just got here, which is 18.89. Okay, now after finding this value, which is here, okay, after finding this value here, you need to find another value for this one. Remember we said this part now is the first one which we did, and the calculations are here now, just this other part. So this is the demarcation here. Now we have this value here. Okay, I needed the other. Okay, so now to find the next value of this S1 minus, which is this one, you convert this into million meter cubed. So how do you find? Let me also include that formula. Let me write the formula. So to find the next value of it's not writing again. Okay, to find the next value of S1 minus Q1 change in time over 2, you simply subtract. So you say S2 plus Q2 change in time over 2 minus Q2 change in time. Okay, change in time. Now what does this mean? This means that you can see this arrow here. So this is our, please, this is our, look at my case or arrow something. This is our Q2, right? So then this is our S. So the difference between these two is my one zaya, then in my minus. So I'll be using minus to mean this one and plus this one. Now to find the next value of minus here, you need to subtract the value that you get after converting it from this value. Now when you multiply this 18.89 times the change in time, which is 10/1800, then you divide that by a million, so that it becomes million meter cubed. Then you subtract the answer that you get from this figure here. So what we are saying is 3, to find the next value for here, this value here, you say 3.94, this value here, minus this value which you have found 18.89, okay, times change in time 10/800 over a million. Okay, I would have just written 10 to the power 6. Okay, so when you punch this value, when you punch this whole thing on your calculator, you're going to find this number here, on my caster here. Okay, then when you find this number, the formula, what is the formula telling you? The formula is saying to find this unknown value, you add this and this. Okay, you add this and this. So now we know again. So when t is equals to 6, again we have two things that we know. We know the average, this part here, and we also know this part here. So you add this plus this, okay? You add this plus this, you get this number here, 4.141. Then 4.141, again in linear interpolation, you look for two sets of numbers which satisfy this. So this is, or the numbers where this 4.14 is in between. So you come here, you realize that 4.1 is in between these two numbers, this number here and this number here. So this 3.9 is less than 4.1, but 4.1 is less than 4.6. So it is in between here. So again, using this formula here, linear interpolation, you put your x values. In this case, your x2 is 4.628 minus your x1 3.988. You put them here. Then y2 which goes with the highest value for x, which is 46 minus 20, okay, and then plus 20. So when you punch that number, you're going to get the next value of q2 again. So the process just repeats itself until you fill in all the figures, okay. So again, here the q2 we have 26.22. Convert this into million meter cubed. You multiply this 26.22 times 10,800, which is the time difference or time interval. Then you divide it by a million. Then subtract it from 4.141. The answer that you get is this one here for the next time interval when t is equals to 9. Again, you have two known things, this and this. You add them, you get this value. This value, linear interpolation, you do use this formula here, which we have already established, and you understand it. You get 50.33. Okay. Again, 50.33, convert it into million meter cubed. So you multiply this 50 times 10,800. Then you divide it by a million. Then subtract the answer that you get from 4.55. Then you get this number here for the next time interval when t is equals to 12. So you have two things which you know. So you see 8.826 plus this one. Then so let me even indicate here that there is a plus. You are adding, there is a plus this. So this one plus this one. So you are adding these two throughout your calculations, okay. So again, when you find this, you add the two, they give you this one. This is your x now. Linear interpolation, again, you find the value of q, 55. So 55, convert it again into million meter cubed. The answer that you get, you subtract it from 4.88, you get this value here. Now you need to be very careful, because when you're writing, you may sometimes it repeats, like these values are repeating. You find that maybe this interval here, this statement is satisfied maybe by the value of x is here about maybe 3 or 4. So meaning you'll be using the same values, okay. So like the first one we used this, is the second one used these two, also the third one used the same. But as you go, maybe you change from here to here, maybe your next value of x is in between here. So when you change, you might be tempted and put y1 as 20 when actually it is 46. So you need to be very careful, okay. So now, after doing that, you fill in the table using the same method up to the end. Now you realize that okay, now we have filled the table. So let's start answering the question. Now question A, route the inflow hydrograph using the modified pools method and determine outflow hydrography. So outflow hydrograph, we have already done it, where is simply Q2 here, against the time here. Okay, so you can plot these two. That's the inflow hydrograph. So this and this one. Okay, in fact, we're not even plotting, we have just established it. Now we have calculated it. We have Q2 and time 1. Okay, time and Q2, sorry. Then question B, a maximum reservoir elevation. Now this one I'll explain it in part 2. For now, let's go to C, peak outflow discharge. So peak outflow discharge, you come here and you look which one is the highest number. So the highest number here is 59.73. 59.73. That is the answer. That is the highest. Okay, so you've answered the question C. So 59.7 meter cubed per second. Then D, attenuation and time lag. Attenuation, simply the difference between the two peaks. Now your inflow peak, if you check here, you realize that it is 80, and your outflow peak is this one, which is 59.7. So attenuation is simply the difference between the two. So you say 80 minus 59. That is your attenuation, which is okay, we have written it here, which is 20.3. Okay, 20.3. Then E, time lag. Time lag also is simply the time difference between the two peaks. Okay, so peak number 1, the time was 9 hours. Then peak number 2, the time was 15 hours. So the difference between these two times will give you time lag, which is 15 minus 9, 6 hours. So what it means is, it simply means that when upstream it was at its own peak, the volume of water was around 80.80 meter cubed per second. That was the peak. It took 6 hours for the downstream to have its own peak, which was 59. Okay, so it took, after 6 hours, the peak downstream was 59, and after that it dropped. So meaning water was just accumulating until that peak was reached, and then it started going down. So you remember we said it is very important, because then at this particular point, if we were given even the speed of water, we would have calculated the distance at which it covered. Okay, then we know exactly location where that peak will happen, and then we are able to plan. You say, okay, looking at the geomorphology, looking at the landscape, looking at the soil type, looking at all the environmental factors which promote floods, is this location able to contain this amount of water? What will be the implication of this? Then after that, then you start even planning. 6 hours is a lot of time. Sometimes you may have 24 hours, sometimes even 2 days. Then you can plan. You say, okay, we need, maybe if you are to bring those things to, like maybe you want to start cleaning drainages so that water should move out as quickly as possible. You do all those things, you know, sweeping the cities, to avoid maybe, you know, erosion and all those things. So that is why we said it is very important. Now you are forecasting based on what you have. You are forecasting the flood. You say, okay, if here I have this, then after 6 hours I'll have this at point B. Okay, now we have answered the questions. Now let's go to part 2. We'll go to part 2 so that I explain a bit where you can, I think it will not take more than 10 minutes, but I'll use the example. I'll use the exercise that you are given as an example, okay, so that you see, because these same values, if you find it tedious to use linear interpolation, then you can use the graph. The graph is just quite involving when you are graphing it. Once you are done graphing it, everything is easy and very fast. You can find these figures, okay. But also linear interpolation, there will be no need of you writing all these x, y1, y whatever. As long as you know, you can see the figures, you can just punch them on your calculator, and then within no time you are done. Okay, thank you.